Okay, you have the opportunity to turn something in to me today. Is that correct? Okay. I will accept that now. While that's happening, I have a stack of stuff I'm going to pass around.
So the thing is just 2 columns?
Yes, that's right. Well, I gave you 2 there and 2 here. 2, if y'all hadn't done well on the quiz, I gave you an opportunity to do those 2. Remember that?
Yeah.
And then there was the 2 on the board.
And are those together?
Separately.
Sort of it?
Yeah. Yep.
Give you all 4 of them?
Yep. I'm sorry?
Give you all 4 of them?
Yes, please.
Okay.
And then let's see here. I have... Okay, so I'm going to pass around. Your grades should have been updated. Do y'all see your grades change? Okay. I'm going to pass these around. There's no grades on these, so you won't, people can't see your grades. You should have, I think, 2 things in here. So make sure you go through the whole stack. Pass that around. Thank you. And then anyone turning in? Yes? Okay.
Requires points because of that mistake.
Did you put it on here? No?
I wrote it on.
Where? You did. Okay, 5 points. There you go. Thank you. Anyone else? Okay, Rushton, Indiana, Ariana, Carlos, Ian? No? Anyone? Who are you? Ian. Okay, this is the exam. I just have this, I've had it for a while, so. Rushton, Indiana, Ariana. Oh, I'm sorry. That's from way back when. Okay, let me get this out of here. All right, anybody else turning in? That stuff from last time? No? Okay, what in the world are we doing? We have an exam coming up when? 26th, which is next Thursday, right? Next Thursday. And let me get all my markers here, sorry. Is that for me? Thank you. If you feel good about it, it's okay. Without it? Okay. How did those problems go? Any issues? All right? Y'all ready to move on to bigger and better things? Yeah? I plan on getting you the review sometime this week, hopefully by Thursday. Yeah. All right. So I have a problem for us to start on. And you'll need to pay attention closely to what I assigned for homework because we're going to not follow the schedule. We're going to skip a few things in the schedule. So I don't want you to just especially if you miss class, for anyone who's watching the video, don't just be doing the homework off the schedule because we may not have covered that, all right? So I have a problem here that I put together before class for us to look at and try and sketch. And you're going to see we're going to run into a problem on this. So sketch f of x equals, let's see, x to the 4th minus 3x cubed minus 6x squared. What's that sound? Is that you?
Yeah.
No. It's like music.
Just drilling.
Is it drilling?
Yeah. I heard it in my car.
Huh, weird. Okay.
They're doing some work.
Okay.
Near the elevator.
Sounds like music to me. Minus 40. Okay, here we go. So let's sketch this. This is going to be the last polynomial function we do. And then we're moving on to the next topic, all right? So we look at that. Okay, what are the steps to sketch? first thing we do is we identify the end behavior, right?
Yep.
And for that, we need to identify the degree in the leading coefficient. The degree of this polynomial, right? Degree is 4, and that's even. The leading coefficient is what? 1, which is positive. And once we know that, we go to the table that I gave you, right, that you can have on your test. We'll talk about that more on Thursday and next week. So that means both sides go up, and in the middle, you're not sure what happens, right? Okay, what's the second step? X-intercepts and the multiplicities, right? And this is going to tell us where our function hits the x-axis and where it touches and where it bounces off and where it crosses through, right? But to do this, we have to set the function equal to 0. We have to actually set this big, ugly thing equal to 0. That's somewhat annoying, isn't it? Is it just me? That sound? All right, so we need to see if we can factor this. First step for factoring is GCF, right? Do you see a greatest common factor? No, right? There's not an x term in each of these, or there's not an x in each term, and there's no number I can pull out. So I don't have anything I can do. So I'm going to go to my synthetic division, and I'm happy to see that there's a 1 here, right? Because the 1 here tells me that my list is going to come just from the number 40 in the back. So I've got to write all the factors of 40. So I'm trying to make my list here. All the factors of 40. 1 and 40. 2 and 20. Right? 3? 3 go in there? No. I don't think 3 goes in there. 4. 4 and 10. 5 goes in there, right? You just make the rest of your list, okay? Because I know this is going to work in the very beginning, all right? All right, can I continue? All right, so now, let's do synthetic division. Do you want me to show you it not working, or do you want me to just get right to what works? Right to what works? Show you not working? It doesn't work for 1. It doesn't work for -1. It doesn't work for 2, but it works for -2. All right, so I'm gonna go ahead and go straight to the synthetic division with -2. And we have 1, -3, -6, -12, and -40. And keep in mind here, we don't have any missing gaps, right? Like we have, for every power of x from 4 down, right, we have something, so we don't have any zeros up there. Remember last class, you have to pay attention, make sure you don't have any zeros. All right, so this should work. Let's see, 1 comes down. -2 times 1 is -2. -3 plus -2 is -5. -2 times -5 is +10. -6 plus 10 is 4. -2 times 4 is -8. -12 plus -8 is -20. And -2 times -20 is +40. And we get 0, which is what we wanted, right? Okay. So now what does this tell us? I don't want you to lose sight of what this tells us. This tells us that this can now be rewritten as x, what? X plus 2, right? Plus 2. That comes from this number right here, x plus 2. And then the rest of the polynomial is this, right? Is this right here. Now, I have -20, and then this is going to be a 4x, and then minus 5x squared, and then plus x cubed, right? That's what this means. So I have x cubed here, minus 5x squared, plus 4x, minus 20. All right, so that's what I know so far, right? That's what I know. And then I try and break this down. Unfortunately, that means I need to continue my synthetic division, right? And so I'm going to continue synthetic division, and I'm going to continue using my list again, right? I'm not going to do a new list. And to save you time, right? Well, what would be the next number I try? I try -2 again. It's not going to work. And then I go to 4. 4 won't work. -4 won't work. 5 is the number that's going to work, all right? 5 will work. So again, not showing the things that don't work, just getting right to what does. Okay, so I'm going with 5. I'm working with these numbers here. Let's see, 1, 5 times 1 is 5. Ooh, 0. Okay, 5 times 0, 0. 4 plus 0 is 4. 5 times 4 is 20. And you can see that you get 0 there. All right, so far okay, I think, hopefully. Yeah, so let's see, what does that tell us? This tells us that this is x plus 2. And then we use this number, x minus 5. And then be careful here. This is your number by itself. This is the number in front of x, so we won't have an x term. And then we have 1x squared. So it's just going to be x squared plus 4, right? And then, sorry, I forgot to put the equals 0 on this, because remember, it was an equation, equals 0, equals 0, equals 0. Let me just make sure I'm recording. And yes. All right, so that's where we are, right? And we run into an issue here, right here with the x squared plus 4. Because x squared plus 4 cannot be factored. How do I know that? Well, we've talked about special factoring, types of factors, and if this were x squared minus 4, then of course we could do difference of squares, right? But a sum of squares, there's no way to factor, all right? But I still need to figure out where it's equal to 0. So let me continue, all right? I'm going to erase this. I'm going to erase this. And let me try and set each of these factors equal to 0 right now, all right? I set the x plus 2 equal to 0, right? And that gives me x equals -2, all right? And then I set the x minus 5 equal to 0, and that gives me x is 5. Then I have to get to this point where I know this does not factor, right? So I'm going to try and set it equal to 0. And that becomes an issue because I move the 4 to the other side. I get some number squared is -4, right? And that's going to have no real solution. That's what we've talked about in this class, right? No real solution. How does that impact things? Is that going to, I mean, because we need to know about crossing and bouncing and things like that, right? Like what's going to happen. How does this impact things? So let me show you. If we solve this, which we have never done in this class, I've stayed away from imaginary numbers, right? If we solved it, we would take the square root on both sides. You would have to do plus or minus. This would be x. This is plus or minus the square root of -4. And what you would get here are two, what we call complex numbers, complex or imaginary numbers. Right? So there's no real number solution, but there are imaginary number solutions, and there's 2 of them, right? There's 2 of them. How do I know there's 2? Plus or minus, all right? So this is where the I would come into play. Now, there's an entire section in this book about what are called the complex zeros, or the complex zeros of a polynomial function. I am choosing not to study that, and I've told you before because the reason is because you don't see it again, right? Like I told you, in pre-cal you won't see it, in Cal 1 you won't see it, in Cal 2 you won't see it, in Cal 3 you won't see it, right? You don't see it till past differential equations in linear algebra. Then you get into a class called complex variables. So you will have time to revisit this, and by the time you get to that, your mathematical, if you even wanted to study it, this is complex variables, not really a class most students take. Some engineers do it, and all math majors have to. But by the time you get to the imaginary numbers later, you're like at a completely different level mathematically. Like it's real easy for you to absorb it because like you're just in a different place. Does that make sense? So I don't think it's worth us spending an entire day on a section that you're not going to see again. Probably most of you won't. So I'm okay with leaving this behind. The reason I'm pointing it out is that I want you to see that this is not going to impact our ability to graph things, all right? And so how do we deal with this? Once we see there's two complex or imaginary numbers, because we see we have a square root of a negative, then what we do is we ignore this, okay? We're just gonna ignore it. Okay, we're just gonna ignore it. And that means I'm gonna base all of my graphing off of these two things right here. So I'm ready to start drawing, but I need to know if I bounce or cross. So at this x equals -2, do I bounce or cross? Cross y? The multiplicity of 1. You get that from where? That power right there on the factor, right? That has a multiplicity of 1. So does the x minus 5 factor, has a multiplicity of 1. Those are odd numbers, and because they're odd, we bounce. The big mistake I'll see students make is that they determine the bouncing and the crossing off of that number. And they say, oh, that's odd, I'm going to cross. No. Why did I put bounce? Sorry. Y'all are like, what the hell are you doing? It's cross, right? On both? Sorry. Cross, right? But they'll say, okay, look, that's an even number. So they'll say, oh, I must bounce there. No, you don't base it off the number. You don't base it off the x-intercept. You base it off the power on the factor where that x-intercept came from. All right, so now I draw it. Here we go. I put my two x-intercepts, -2, +5, like this. And then it went up, right? Up. So it went up over here and up over here. And I crossed through it both. So I come down, I cross through, and then I come back through and cross through. So it kind of looks like a parabola. It's not exactly a parabola, but it kind of does. We don't, with polynomials, it's not that important. Yes? Is that the stack of stuff? Y'all thin that out real good for me. Thank you. Appreciate that. That was becoming a nuisance to me. Anyone else want to go through the stack of old quizzes and stuff? Anyone else? Okay. All right. So let's look at Desmos on the screen over there. I just want to graph this and show you that it really, in fact, did not have any impact on things. So let me go a new blank graph. So if I graph f of x equals x to the 4 minus 3x cubed minus 6x squared minus 12x minus 40. Okay, there's the graph of this function. I have to zoom out quite a bit for you to see this. There we go. See, so it's not quite a parabola. Do y'all see it's not quite a parabola? That little wiggle that we have there at the bottom, this other factor is having an impact on things. But again, in this class, we're not concerned with that part of it. Cal 1, you will figure out where that wiggle happens and how low it goes and all that stuff. But we have the general idea, right? To the left of this, we're above the x-axis. Between here and here, we're below. And then to the right of 5, we're above. Okay? So again, we're not going to do anything there with complex numbers. We're going to move on. And we're going to start rational functions now. All right? So one thing I did not do, and I'm going to try not to go too far off on a tangent here. I don't know if I think I did talk about this. If we go back and we kind of revisit everything that we've done up to this point in terms of functions, right? When it comes to functions, the things that we should be able to sketch right now, well, linear functions, right? We should all be able to sketch linear functions. That's any function that would look like f of x equals mx plus b. We should be able to sketch quadratic functions, right? That's all functions that look like ax squared plus bx plus c. And remember, there was two forms for quadratics, right? It was the standard form, and there was another form called the vertex form. Yeah, it was that form, right? So this is standard form, vertex form. We should all be comfortable sketching both of those types, right? And now we have polynomials, right? And that's what we just studied, right? And so, we know polynomials can look really different, so I can't give you like a general, I'm not going to write a general form of it, but all of these we should be able to sketch, right? And the steps for sketching these are all different, right? How you sketch a line is different than how you sketch a parabola, which is different than how you sketch a polynomial. Quadratics, there was a lot of detail in there, right? Does it open up or down? Where's the vertex, right? All that. But here, it was more of just like what we just did, general idea of what's happening. What I want to emphasize right now is why we study these, right? So lines, when you graph them, right, they're lines. Anything in the real world that grows at the same rate all the time, like, for example, I'll give you an example of a linear function. Yeah, you hope they're going up like that. Something like this. Let me do this. Let's say I write this function here. That is a linear function. Okay, it's kind of like f of x equals mx plus b. This is like f of x equals, here's the slope m, and this is our variable x. This function right here is if you work and you make $15 an hour. That's your pay function, right? If you make $15 an hour, then if you work 0 hours, you make $0. 1 hour, you make 15. 2 hours, you make 30, right? So this, if I graphed it, would show you how much you get paid over a certain number of hours you work, right? Anything in the real world that grows constantly, linear functions are good for. Quadratics, you remember me talking about this? Satellites and bombs and stuff, right? We talked about that. So we've already looked at different examples of that in the real world. Polynomials, that would be more like stock market. Anything that waves, goes up and down, has fluctuations, right? Polynomials. Now what we do is we study rational functions. And the thing about rational functions is that they behave in a way that none of these do, all right? So again, it's like we have something in the real world that we observe, and what we need is a function that kind of models what's happening, right? Stock market, polynomials are good for stock market. Things flying through the air, quadratics, right? Things that grow constantly, linear. What are rational functions good for, right? We don't know yet, right? I'm about to tell you. So I'm going to motivate this whole idea of a rational function with one of my favorite quotes from a movie. Okay, I'm going to put the quote up here. Let's see if anyone can figure out the movie. The older I get, the fewer students get this, all right? So here's the quote. And I might not be exactly right, all right, but it's something like this. On a long enough timeline, the survival rate for everything, don't go look this up on your phone, drops to 0. Okay. On a long enough timeline, the survival rate for everything drops to 0. Star Wars? Yeah. No, not Star Wars. Anyone know it? Think?
Back to the Future.
No. I'll give you the main characters, main actors. Ed Norton Jr. and what's his name? Brad Pitt. No?
Is that the one where he's super smart?
I don't know.
He like solves the equation on the board.
No. I've never seen him in that movie.
Goodwill.
Not Good Will Hunting. Oh, you're thinking Good Will Hunting.
Yeah, Goodwill.
I don't think either one of those actors are in that movie. Fight Club? Have you ever seen Fight Club?
Yeah.
No? How many of you seen Fight Club? Okay. You've heard of it? Okay.
This is in it?
Yeah. So in the movie, the main character is, his original job in the movie in the beginning is that he works for an insurance company, and basically he helps figure out whether or not, I'm not going to get into it, but he works with statistics, all right? And so this is one of the quotes from the movie. On a long enough timeline, the survival rate for everything drops to 0. So I really want us to think about this quote from this perspective, all right? I'm going to draw a graph here, or X and Y axis here. I'll make this really, really long. Okay? And this is going to be time. And let's say we measure this in years. Right? In years. And then over here, I want to put probability. Probability that you're alive, that a person is alive. Okay, so what we're looking at here is just a general picture of just talking about humans in general. Okay, all humans on this planet in general. At time 0, we're going to imagine that somebody is born, okay, or they are alive. And we're not going to debate when life begins and all that shit. We're not getting into that. We're just going to say somebody is alive, okay? So at the very beginning, right, at the very beginning, I'm going to put 1 here. I'm going to put a dot because the person is alive. The 1 represents 100%. There's a 100% chance that that person is alive because I just told you they're alive, right? Okay. What happens as I go this way? So what's the probability that a human being in general will live to see their first birthday? I don't know, less than 100%. Would you agree? But probably pretty good. Probably pretty good. The first, I think, 2 years of life are actually more risky. Once you get past 2 years, you're actually, like, it's a good sign if you make it through your first 2 years. So I'm going to say that maybe after about a year, I don't know, you're somewhere in the 80s, 90s, who cares? Somewhere around here. And then after 2 years, maybe it bumps up a little bit because you know what? If you make it through the first year, it's a little bit higher. And then it goes up a little bit, okay? And if I connect this, something like that. With me? Okay. 10. What's the probability you make it to 10 years? You, a human, right? I mean, has it come down or gone up? What do you think? Do you think there's a better chance you make it to 10 than you make it to 1? Or 2?
Yeah.
You could get, what? Hit by a car, you could drown, you could, right? There's a lot of things that could happen to you, right? So your probability is going to drop off. Generally speaking, right? Things can happen, right? Shit happens. Okay, yeah? Okay, what about 50? This is not going to be to scale, okay? What about 50? Lower, for sure, right? And again, I'm not caring too much about the percentages. It's the idea, okay? Yeah, with me? 80? Lower for sure, right? Okay, and again, we're not talking about men versus women, right? Women usually have longer lifespans than men, right? In the United States, are we in the United States? Are we in a different country, right? Third world country, first world country? We're not doing any of that, just generally speaking, right? 80, yeah? There's a chance. Most of us feel pretty comfortable that we might make it to 80, yeah? 100? Lower? Pretty low? Okay. Here's where things start to get interesting. Let's read this quote. On a long enough timeline, the survival rate for everything drops to 0. Okay? Do you see what's happening here on this timeline? This is a timeline, right? This is a timeline. On a long enough timeline, the survival rate for everything drops to 0. Drops to 0. Does it say reaches 0? Drops to 0. Let's understand that. Let's go with 110. Chances human is going to live to 110. There's a chance. I think somebody's done it before, right? There's a few. So, there's a chance, right? It's pretty small, but, and I don't know if any of us want to be around that long, to be honest, right? Sorry. Maybe you do. Maybe you do. All right. Okay. 110. What do you want next? How about 150? Okay. So nobody that we know of has lived this long, right? But we're talking about probabilities, right? Probabilities, when you talk about a probability, you're talking about something that has not occurred, right? The question is, can it occur? Do you think that somebody could live to be 150? Is it possible? Can you say it's not possible? Can you tell me 0?
No, you can't.
You can't tell me 0, but you can tell me the probability is what? Really, really low. What do you think is more likely? How about, let's look at it this way. Let's go back to 110. What do you think is more likely for you? That you're going to live to 110 or that you're going to win that big lottery that's like $1 billion lottery? What do you think is more likely?
110.
You think you're more likely to live to 110? Okay, how about the 150? Do you think you're more likely to live to 150 or to win that lottery? That's a tougher one, right?
Technically, people have already won the lottery. No one's made it to 150.
Nobody's made it to 150 that we know of, and people do win the lottery. I think it's probably more likely for you to win that big lottery than to make it to 150, right? But there's still a chance, right? Yes? Okay. All right. So I'm going to say this is like, I'm going to use this word, infinitesimally small chance. So this is a very small number, and it's getting really small, really close to zero, right? It's not there yet, though. Okay, let's go crazy. 1,000. Can you say zero?
I don't think I got it.
Can you say zero yet?
No.
I mean, technology can be far.
Okay, technology, right? So this is the idea. The idea here is that if you look at the functions that we've studied in this class, like lines, right? Parabolas, right? Polynomials, right? Do any of these behave this way? Where you have something that's kind of like dropping away and getting closer to something without actually getting to it? None of these do that, right? None of these do that. So if we want to model something like in the real world like this, we can't use anything like this. We need another type of function, right? Let's keep going though. I want us to really understand this. How about if I throw a couple more zeros on here for you? The question remains, like, can you ever say zero? Is there ever going to be a place where you tell me zero?
I mean, the end of the universe. I mean, that's where you
Okay, so like if you go to infinity, right, maybe?
like a Google, like time, you know.
So maybe, but here's the thing, here's what I would argue, is that even though you may go out 1 billion years, right, and say no human's going to live to be 1 billion years, you can't say zero because there's a small enough number to represent that probability. Let's think about small numbers for a second. The lottery. Chances of me winning the lottery, that big one, right? The big one. I'm not talking the scratch-off ticket. I'm talking that big lottery, right? Chances pretty small, right? Could it happen? If I play it, could it happen? Okay. What's the chance of me winning that lottery twice?
Pretty low.
Even smaller, right? But could it happen? If I played twice, could I win twice? Yes? What's the probability of me winning the lottery twice, the next week getting struck by lightning and living, and then winning the lottery again? Could happen, but
More like Vegas.
I mean, we're talking, see, this is what I'm talking about, infinitesimally small numbers. There is, for this right here, there is some probability, but it's probably 0.000000000000000000001. You know what I mean? Like, we are never going to run out of numbers. We're never going to run out of numbers that keep getting smaller, right? You're never going to reach zero. So what happens here, at the end of this, right, at the end of all this, what's happening here is that this graph